So, for my IP Physics review video, I just wanted to review deriving these four fundamental equations for a parallel plate capacitor. So, to start off with, I want to derive the electric field between two plates of a parallel plate capacitor. So, to do this, we'll just look at one plate, and we'll say it's the positive plate, and we'll apply Gauss's law. So, we will create a Gaussian surface of a cylinder that goes through one plate of the capacitor. So we're going to be assuming that the fringe effects are negligible, so the electric field is pointed straight out from the plate at all points. So that means that the flux through the sides of the cylinder is going to be zero. Now the other thing to note is since we have another plate over here, and that represents our negative plate of the capacitor, we know that anywhere outside the capacitor, the electric field from the positive plate and that from the negative plate are going to cancel out, and so all of the flux through this Gaussian surface is just going to be through the end cap. So we'll give that some area A, and we'll start applying Gauss's law. So, first off, looking at this closed integral, since our electric field is perpendicular to the surface and constant across it, electric field's going to go away, and we're just going to be left with electric field times the area of that end cap is equal to the Q enclosed over epsilon naught. So now we just look at the charge enclosed, and for that we look at all the enclosed charge is going to be on this inner circle right there, and it's going to be, so the enclosed charge is going to be some proportion of the total charge on this plate, and that proportion is going to be little a over big A, because that's almost like the percentage of the plate that we have within this circle, and so that is the charge that we have within that little area A. So if we substitute that in, the first thing to note is that the area of our Gaussian surface is going to cancel out, and that makes sense because you wouldn't expect the area of our arbitrary Gaussian surface to have an effect on the system. So we're left with just the electric field equals Q over epsilon naught A. And the total charge over the total area of the plates, that's just going to be the area charge density. So we can make that substitution, and we're left with our first equation. So now we're going to move on and discuss the equation for just the general capacitor equation and the equation for capacitance. But before we do that, we have to look at dielectrics. So if you imagine taking a capacitor with a positive plate and a negative plate, the result of inserting some dielectric with some dielectric constant kappa, that's an awful kappa, but whatever. The result of this is that it scales down, because the electric field between these 2 points, some constant value, and the dielectric scales that down by some amount 1 over kappa. So the new electric field, once we insert that, is going to be the electric field over kappa, which for us is just equal to Q over kappa epsilon naught A, using this value right here. So, using that value, we are going to derive an equation that relates the voltage across a capacitor to the charge on the plates. So you know that the change in voltage is the negative integral of the electric field times dx. Now, before we substitute in our electric field and add some bounds of integration, we need to discuss where we're integrating. So it makes sense that the bounds of integration are going to be from some value x equals 0 to some distance equal to our separation d. And so it makes sense that our change in voltage is some negative integral from 0 to d. But we need to discuss the electric field for a moment, because this right here is actually just the magnitude of the electric field. Electric field is a vector. So looking at this capacitor right here, electric field would travel in this direction. So if you integrate in this direction, you're going to get a negative change in voltage because the energy decreases when you move with the electric field. We're going to be integrating in this direction, and so as such, we're moving against the electric field, and so we have a negative sigma over epsilon naught, and as you can see, those negatives are going to cancel, leaving us with a positive change in voltage. So we're going to substitute in our value for electric field that included kappa to get the integral from 0 to some distance d of q over kappa epsilon naught a dx. Now everything in this integral is a constant, so we can take that out and evaluate the integral, which is just going to result as then the integral from 0 to d of dx, or d. So we get that voltage equals q times the result of the integral is d over kappa epsilon naught a. Now we're going to rearrange this a bit to solve for q. So we get that q equals kappa epsilon naught a all over d times the change in voltage. And now this is a pretty significant result. It's cool to look at because you see that the charge on a capacitor is directly proportional to the voltage across it for any given capacitor with these constant sort of conditions on it. So since that's a cool result, they're proportional, we decided to assign this proportionality constant to some value c, and we call that the capacitance. And as we know, it's just a measure of how much a change in voltage across the capacitor affects the charge stored on it. So once we call this capacitance, this first equation simplifies down quite a bit to just be equal to Q equals C times a change in voltage. Now, that makes our next two equations, and we have one left. So to wrap this up, I'm going to be using the results that we've gotten to solve for the energy across the capacitor. So let's get ourselves some room. Now, we know that energy is defined as let's just discuss voltage for a second. We know what voltage is. It's a change in energy per charge, or I guess that's change in voltage. So our voltage, let's just say, is energy per charge. So knowing this is the definition for voltage, if we know our voltage across our capacitor, and we know the charge on the capacitor, then at first what would seem intuitive to do is just to say, okay, if we multiply our voltage times our charge, then we get energy. And I guess in this case it's potential energy, so we use a U. And that would seem right at first, but it's not. Because we have some charge Q on our capacitors, and it's across a change in voltage of V. And so at first it would seem like this is our potential energy on the capacitor, but we know it's actually 1/2 QV. So the reasoning behind that is because if you consider the capacitor, the thing that's causing, in a way, the voltage across the capacitor is the charge that's on it. The voltage is a function of charge. And so at first, if you imagine our two sides of a capacitor, and you imagine we connect them, and some tiny little dq goes from one side of the capacitor to the other. Well, this dq just gained an energy equal to V dq, but the total voltage just decreased by using our equation. The new voltage is now going to be the original voltage minus that dq over C. So as our charge, as we accumulate more and more charge moving, the voltage is going to decrease. Since they're proportional, it's going to decrease linearly, and so the voltage is going to start at some value V. It's going to go down to some value 0. It's going to go down to 0, actually, the change in voltage. And so it almost makes sense that since it's linearly decreasing, we have 1/2 of what it would be if it was just at its max the whole time, because it's in a way it's the average. But to prove that a little bit more rigorously, we can use integration. It makes sense. Anytime we have these tiny little infinitesimal values that are changing and affecting each other, and we have to sum them up, it makes sense to turn to an integral. So, knowing that the energy is our voltage times our charge, we can say it's the integral from the charge equals 0, we're going to say, the charge equals 0 to the charge equals our Q max, because we're imagining these tiny little charges leaving, of the voltage times dq. And the voltage is Q over C, so we get Q over C. And it's a little bit weird to integrate with respect to Q. You just have to remember that we're summing up tiny little Q values that are changing. So we get, and I suppose technically this would be from Q to 0, since that's where we're starting and ending. And then we'll get a negative energy because the energy is being released as the charges move. But we're going to do it the other way around because right now we just care about the magnitude of charge on the capacitor. So evaluating this integral, we get the 1 over C's constant, so we pull that out. And then the integral of Q with respect to Q, I suppose this is capital and that's lowercase, so we can swap that out so that our variables actually match, is 1/2 Q squared. So there's where our 1/2 comes in. So we get 1/2 Q squared, and we're evaluating it from 0 to our maximum value Q. So once we evaluate it, we get the energy is equal to Q. If you plug in 0, then this term goes away, so we just have to worry about the max. And we get Q squared over 2C. And you realize this is just an alternate form of our equation. We can swap out this Q over C to be equal to the change in voltage. So we get that the potential energy across it equals, one of these Q over C's becomes voltage, and there's a Q left over, so 1/2 QV. And there is our value.